Hello amigos, so now let's complete the chapter with this accelerated flight and the last lecture of UAV and UCAVs. So in accelerated flight we have VN diagram left, and let's see what VN diagram represents. The VN diagram specifically tells us about the envelope of an aircraft in which the aircraft will be flying. If the aircraft fly away from this envelope, away from this enclosed envelope, or if the aircraft fly outside of this closed envelope, that is A, B, C, D, E, then it will have to face consequences that it will have structural damage, or it will have stall, it will stall. Okay, so let's discuss it. And here this graph basically is for a typical jet trainer aircraft, and VN diagram XY axis, as you can see, is X axis V and Y is N. So similarly we have the corresponding values of N, positive N on this axis and negative N on this axis, and velocity is increasing in this direction. So what is happening over here, as you can see, this AB line and this AE line, above which or below this are the stall area. Okay, so here if the aircraft is flying below this AB line or above this AE line, curve lines, so the aircraft will not stall. Okay, that is, if the aircraft is flying at this velocity and the aircraft is having this much load factor at this velocity, then it will not stall. But if the aircraft is flying at this velocity, but it might have a load factor higher than the corresponding load factor over here, so it will stall. How that can happen, let's see. As you can see, this is the lower velocity region, and in this region we are talking about accelerated flight, and for the low velocity regions, load factor is given by Nmax, or say N equals L by W, we know, and Nmax, when lift value is substituted over here, we get half rho v square CL max divided by W by S. This is for low speed value of Nmax that we obtain for low speed, okay, for low speed flying aircrafts. So we have Nmax value for high speed flying aircrafts that corresponds to the structural limit. Here the Nmax value corresponds to the CL max limit for low speed flying of aircrafts. So over here, if let's say the aircraft is flying with V1 velocity and it was first flying at a value this, okay, at this value it has velocity less than 200, low velocity, okay, it is in miles per hour. So, and at one point it is flying, okay, and then moves, and then at the same velocity the value of load factor is increased by increasing the CL max. So we obtain the value of Nmax at 0.2 then. So the maximum value of V1, the maximum value of Nmax at V1 velocity is at 0.2 at corresponding CL max. So if this CL max is further increased by increasing the angle of attack of the aircraft, then it will reach up to a 0.3, where the load factor will be higher than this load factor, higher than 0.2 load factor. And above this load factor, that is load factor at 0.2, let's say it's 6. If load factor is higher than 6, then we know if CL max is increased above the stall limit, then the aircraft will stall. That is, the aircraft will experience a drastic reduction in lift, and at that point we will see the maximum load factor is given by this 0.3, and the aircraft will stall. Similarly, when the aircraft is flying with a negative lift, it will experience the stall below this AE line, similar to the AB line. Okay, so now observing the maximum value of load factor with respect to the structural limit. So let's say the aircraft speeds up to a high values. That is, let's say first the aircraft speed has increased from V1 to a value V star. Okay, this V star value is a reference value which is also known as the corner velocity, and this point at which V star is represented is point B, which is also known as maneuver point. And at this velocity, aircraft will have the maximum CL max and maximum load factor an aircraft can experience. If any of these parameters is becomes higher than these maximum values, then the structural damage is bound to occur and the aircraft will disintegrate, or any structural damage can happen. So we never want to experience such kind of experience, okay, such drastic experience. So let's say the aircraft is flying at V star, it will have then the maximum load factor it can experience and the maximum CL max it can have. And let's say the aircraft is moving at higher velocities, so we know that this line represents the maximum Nmax and the maximum CL max an aircraft can have. Similarly, this line represents the maximum Nmax and maximum CL max. Okay, so aircraft will never exceed these limits. If the aircraft exceeds this value of Nmax or CL max, then aircraft will stall. Okay, so these are for low velocity. And moving on to the higher velocities, we have this maneuver point first, and at maneuver point it will have the lowest possible turn radius and highest possible turn rate. Okay, so according to the flight envelope in which the aircraft is bound to fly, it can experience the highest load factor and the highest CL max at this point to make the aircraft turn with the lowest possible radius and maximum possible turn rate. So as the speed is increased, the structural limit is bound to increase. as the speed is increased, the structural limit gets affected. That the speed was, let's say the speed is increased, okay, from 200 it is increasing up to V star, and beyond V star, if the speed is increased, then to fly within the positive limit of load factor, the aircraft have to fly with CL less than CL max. Okay, so what does this mean? That this was the limit at which, that is, at every point on this line, we have the maximum value of load factor as well as CL max. Here as well, maximum value of load factor as well as CL max. But over here, we have maximum value of load factor, but CL is always less than CL max for different velocities. For different velocities at low speeds, the aircraft can fly with maximum load factor corresponding to maximum CL max. But at higher velocities, it cannot fly at maximum CL, but it can fly within the maximum limit of this positive limit of load factor, or within the maximum negative limit of load factor. Okay, so B, C and ED are the positive and negative limit of the load factor, beyond which if the aircraft tries to fly, it will experience the structural damage and the aircraft may disintegrate. So as the speed keep on increasing, let's say the speed is increasing, the aircraft structure may disintegrate with increasing speed, because the G factor or the G force on the structure of the aircraft is increasing exponentially at higher velocities. So at higher velocities, the aircraft will have to consider the maximum velocity below which it has to fly, so that aircraft may not disintegrate, and that limit is given by CD line over here. And this complete is known as the VN diagram, flight envelope. A, B, C, D, E. Okay, this whole is the flight envelope, and it's complete. And let's say we have this point B. Let's observe this point B for the time being, and you will see that V star is given by under root 2 times N max multiplied by W by S wing loading divided by rho CL max. This formula is derived from L equals N times W, lift equals N times weight. And for maximum load factor and maximum CL max, we have this corresponding velocity, which is the corner velocity, or the highest possible velocity with which an aircraft can maneuver in its flight to perform the lowest possible radius and highest possible turn rate. Okay, so with this we have completed the VN diagram, and lastly we have the UAV or UCAVs. So UAV or UCAVs are simply the same aircrafts we have been discussing, that is the same aircraft with no humans inside, and with no humans inside we will not have any human related components in the aircraft. So like passenger seats, oxygen masks or oxygen cylinder, or any kind of component that are related to human, particularly related to human, that will not be inside the aircraft. So how can that be flown? They are flown by the pilots that are on the ground. They are controlling from their remote, you can say. So the point of UAV or UCAVs is that they can command, control and detect as well as track for longer duration at extended ranges. That is, they can perform high maneuvers as well, and they can stay in the air for longer duration. If humans try to stay in the air for longer duration, it will be very tedious for humans. But if an aircraft has to be in the air all by itself, there will not be any problem, and it can fly up to maximum amount. It can extend its range from up to any location, or from any location it can control, detect, command or track. Okay, like in this COVID or lockdown scenario, many people are migrating from one place to another, and to keep track of those, we have to look at those people, and to observe them we are using drones, and those drones are also known as UAVs. So the other thing is about UAVs, that they can be used in military exercises for defense purpose as well, for combat, in combat as well. That is, they can carry armaments, missiles or bombs. That is, they can be used for air-to-air missile or attacking, or air-to-ground attacking and similar fighting scenarios. And they require very high acceleration and maneuverability, so they will experience high G forces that cannot be tolerable by human tolerance. So this is kind of advantage, that if humans were there, they will not be able to tolerate this high G forces. So if humans are taken out, they can accelerate higher and maneuver with high performance. And by high performance, I mean that they will have higher rate of climb, and their rate of climb will be maximum, and their maximum rate of climb will be much higher than any typical passenger aircraft or military aircraft which involve humans specifically. So UCAVs have the highest possible maximum rate of climb, and they have maximum endurance, and also they have maximum range. Okay, and their maximum range is very high than the typical jet aircrafts or other aircrafts. So with this we can see that their turn radius will obviously be lower, and the turn rate will obviously be very high, which is denoted by point B over here in the VN diagram. So with this we have completed Airplane Performance Chapter 6 of Introduction to Flight by J.D. Anderson, and we will do a summary session of this, and thank you.